Let's use this information in order to analyze the operation of the buck converter. A buck converter consists of an inductor which is switched on and off or connected to a source. This is the primary power source of the system. Here is the load. We have a capacitor, which is a filter capacitor. The purpose of this capacitor is to reduce the ripple voltage, that is, to make the voltage at this point across the load, could be your smartphone or any other load, to make the ripple small, voltage ripple. So what is happening here is that this switch is turned on and off. Now obviously this is not a mechanical switch. It is, in most cases, a transistor, a MOSFET transistor, which is turned on and on by some control voltage to the gate. Now here is the control signal, here on, this is the off time, on again, and consequently the switch will turn on, off, etc. It'll go on. So defining this is as T on, and this is the period, we again have a definition of the duty cycle. The on duty cycle will be T on over Ts. The off duty cycle will be the T off. T off is this part here over Ts. Now, usually D on, we call it D. This is the duty cycle of the circuit. Now, here's the period, and 1 over the period is actually the frequency of this operation. So, switch is turning on and off. The inductor is turning on and off. And what is happening here is that if you look at this point, what you'll see is that at one time the inductor is connected to the input voltage, and then it is sort of left alone because the switch is open, sort of the current is interrupted. So here we see this operation. We see that during on time, the V-in is connected to the inductor. This is V-out. So the voltage on the inductor is, voltage here, is actually V-in minus V-out. Here is this voltage. And consequently, the inductor current will go up linearly because V-in is constant, V-out is sort of constant, and then we have a linear slope here. Now, during the off time, what is happening during the off time? Well, there is an interruption of the current, and there is a spike here, or you might say there's a tendency to develop a spike, or the voltage is changing very quickly because you have interrupted the current. The IDT is very high. A voltage will develop here. What's the polarity of the voltage? Well, if this is the direction of the current, this is the imaginary resistor we talked about. Here is the current flowing, continuation of the inductor current. This is plus, this is minus, so this becomes negative. So this voltage will go down. It'll go down, it'll go down, until the diode will start to conduct. Because when the voltage here is low enough, below the sort of break point of the diode, this will be negative voltage. Here it is positive as compared to this negative voltage. So the diode will catch the current of the current. So automatically the current will move from here to here. And consequently it'll go up and down, up and down. Now, when the current passing through the diode, neglecting the voltage drop on the diode, which is like 0.7, 1 volt, depending on the type of the diode, or 0.3, if it's a Schottky diode, we have now a situation in which that at this point, the voltage is approximately 0, while here it is, of course, still V out because of the capacitor holding up the voltage. So we have now a situation in which the voltage across the inductor is now reversed, because at the beginning V-in, and we'll see it later on also, is larger than V-out. So it's a positive slope. Now V-in is sort of 0. I mean, this point is 0 voltage. So therefore the slope is negative and the current is going down. If this operation is in steady state, that is, it's go on and on and on, and it's not moving anywhere, that is, the current is not going up or down, the value of this current and the value of this current must be the same. So that, because then you continue the same way. Otherwise, if you reach only this point, then the next cycle you'll go up. So this is a steady state situation of the buck operation. As we understand then, we have you might say a toggle switch here, which connects the inductor to the input and then automatically to the diode. In fact, one can replace the diode by another transistor, that is, to use two transistors like this. Here's the inductor, here is Vin, and you connect through first one, say Q1, you connect the inductor to Vin, and then you turn it off, and then connect Q2 to ground. So this is a sort of a half-bridge operation, and it's used for many reasons that I'm not going to go into, and this is a practical implementation of the buck circuit. So what we have in the waveform of the inductor, we see a constant rise, we see a drop. As we have said, these two heights must be the same at steady state. This is the slope, the positive slope. This is the negative slope, there's a minus here. And this is the delta I. This is the amount of current that is sort of added and then depleted back. You might say that the inductor is actually storing energy when it is connected to the input. Here it's storing energy, and then delivering this energy to the output. So what would be the ratio of output voltage, or what would be the output voltage as a function of the input voltage? What is the transfer function of this converter? Now, there are two ways to look at it, and I'll start off with a more classical way. The classical way looks at this triangle and at this triangle and calculates the height by knowing T on, knowing the slope, and coming up with the value of delta I here. This is this value here. This is the slope, and this is the time. And then calculates the same delta I from this slope and T off. This is this thing. And then, since these are, of course, the same delta I's, you equate the two, and you come up that the voltage ratio, V out to in, is equal to D on. That is, the duty cycle of this operation, of the operation of the buck, is actually determining the output voltage. So you can control the output voltage by the duty cycle. Now, obviously, the duty cycle cannot be more than one because it's T on over Ts, and the most T on could be, it can approach Ts. This would mean that since the voltage ratio is duty cycle, and duty cycle can be approaching one at the most, transfer function will be, the largest one will be 1. That is, this is a step-down converter. There's another way to analyze the operation of the buck, which is shown here, which is based on the idea of average voltages. We have said at the beginning of this presentation that in stable operation, the average voltage across the inductor must be 0, because if it is not, then the current will keep changing until it reaches very high in values. Now, if we say that this is a stable operation, and we assume that the current goes up and down to the same value, this means that the average voltage is 0. So the average voltage is the area here and plus the area here divided by the period. So if we do this calculation, this is the height and the time. This is the height and time. So this is the area, the positive area. This is the negative area. And since the average must be 0, then these areas must be the same, and you come up with the same expression. So this is just another way to look at it, and I think it's a much simpler and neater way and a more intuitive way to understand the operation of the buck converter. Now, let's see if we understand how this converter actually works. So let's sort of ask ourselves, what happens if the load is changing? That is, you change the load. Let's forget about the transient, that it will take the buck a certain time to stabilize. And so how will this picture look if you change the load? That is, you make the resistor smaller, or you might say that you draw more and more current. Well, if you don't know the answer, let's look at it. What will happen is that you'll see the same sort of pictures in terms of the slopes, but this curve will change. You'll start with a certain resistor. If it is a smaller resistor here, this will go up. And if it is a larger resistor, then it'll go down. Same picture. Why is that? Because the slopes are dependent on voltage. And I've said that we are just changing the load. We are not changing the voltage. Duty cycle is the same. V in is the same. Therefore, V out is the same. So therefore, this slope is also the same. So the only thing that is changing is the level of the current. This is actually the average current here. This is the average current here. And this is the average current here. So as the current is, as the load is changing, the current is changing, and the whole picture goes up and down. So if R is becoming larger and larger, the load, and current is becoming smaller and smaller, this curve will go down. Now, eventually it will hit this point. What happens beyond it? Well, here what will happen. What will happen is that instead of having this thing here, we'll start having this type of a behavior. That is, since the current is very small, this is just too much current. The only way that the system can cope with it will chop this time here, and so this current, the average current, will be smaller. So what will actually happen is that the voltage will go down, the current will go down, it'll hit zero, and then it'll stay zero till the next cycle for this resistor. So the behavior has really changed. We call this discontinuous inductor current mode. This will be opposed to the CCM operation, which is continuous current mode, which we have seen before. Now, obviously, if this current goes very fast, this means that V out, which actually is responsible for this slope, this is V out over L minus. V out must go up so that the slope will be steeper. And indeed, as we enter the discontinuous mode, we hit the point that we actually move from one operation mode to another. Now we can ask the question in a sort of a different way. Suppose we have a operation of the buck, which is okay. Now we change the inductor. That is, the average current is the same, but we change the inductor. What will happen then? Well, voltages are the same, inductor is changing, the slope will change. If the inductor becomes smaller, the slope will come steeper. The slope will be higher and steeper. Eventually, I'll hit this point. So there is an interesting question here from the design point of view. Suppose you need a certain current. You want a certain average current. You don't want to enter the DCM mode of operation, which is, first of all, you're losing control in a sense, and then the current is chopped, so the ripple will be higher. So the question is, what is the smallest inductor that you can tolerate without entering this DCM operation? Well, the calculation is quite simple. I'm not going to go through it, but the end result is that there is a simple expression for it. This is the load resistance. This is the time of T off. This is this time here that you operate. And this is the frequency of operation. Or you can express it in a different way. In any case, this is information you know from the operation of the buck converter, because you know it's the frequency you're running it at, you know what's your load resistance, you know what is the D off because you know TS, and you know what is the D on, so therefore you know what is the D off, and you can calculate the L minimum. Another question is, of course, what will be the voltage transfer ratio, that is the gain of this buck converter when it is in the DCM operational mode. Well, you can derive it. I'm not going through all this simple manipulation math calculation, and you can end up with this expression which gives you a value of the duty cycle, or put it in another way, for a given duty cycle of T on, because you're not controlling anymore this part. This part is sort of controlled by itself. We call it the T prime off, as opposed to this one, which is T off. So you control D on, you know all these values, so therefore the gain can be calculated. Now, in practical application, you still keep, of course, V out to be the value that you need. And this is by changing the duty cycle. That is, there is a controller, there is sort of a feedback that if the voltage tends to change, the duty cycle will change, and automatically you will maintain the desired V out. So let's take an example for the calculation of inductor needed. Now suppose we want an output voltage of 5 volts, we want to operate with an input voltage of 10 volt, we want to be on the borderline of CCM, we have a 10 amp current, and we are running it at 10 kilohertz. So the question is, what would be the L minimum that I need to make sure that for this particular point of operation, the operation will be still in CCM. This is still in, this is a boundary between CCM and DCM. Okay, this is the inductor current, and this is time. So we know the output, we know the input, and the ratio between them is the duty cycle of operation, and D off is 1 minus D on, so it's also 0.5, and you plug it into this equation and you get L minimum of 1.2 microhenry. Okay, interesting to note that if the current goes up and up, that is, if you operate at a higher and higher current, in fact, you can operate with a smaller and smaller inductor. Let's talk a little bit about the output voltage and the capacitor. Now, this will be a large capacitor, the purpose of which is to make sure that the output voltage has a small ripple, depending on the application. Some application would call for very small ripple, some other may tolerate a higher ripple. So here is the inductor current. This inductor current has two components to it. There is a DC part, the average value, and there is a AC part, which is a triangle type. So I can break it into two parts. This is the DC, and this is the AC. Now the DC actually goes through the inductor. There is no DC current through the capacitor. Now, if the capacitor is large and the ripple is indeed very small, then the resistor current will be almost DC with the little ripple on it. So that most of the ripple of the inductor current, this is this AC part, this one here, is actually passing through the capacitor. So the capacitor must be capable of passing this current. This is a limitation of capacitors. That is, one of the specification of a capacitor is how much AC current it can actually tolerate before it'll be damaged due to actually a heat increase. So here is the answer. This is the AC part, and we also already calculated delta I, so we know what is the value of it. This actually brings me to the end of this presentation. I thank you very much for your attention, and I hope that this presentation will be helpful to you. Thank you.